So the results of his studies and observations are really interesting. So when we apply this technique that you define an interval with the ratio 2/1, we'll define an octave, and then from the first note you take an ascending perfect fifth and a descending perfect fifth. If it's outside of your boundary, you transpose it by one octave, or dividing the ratio by 2 or multiplying by 2. So you make sure you're always inside this interval. And you do this note by note, so you generate the next notes. In the next note you take the ascending perfect fifth and descending perfect fifth, and you keep doing this. What we notice is if you take the first 5 notes doing this, we have this scale starting on D, which is a very, very famous scale. It's the pentatonic, the major pentatonic, starting on D. So already with these 5 notes, Pythagoras could explain a lot of the music was doing and was being done at the time. And in fact, a lot of the liras, the tuning, were based on this pentatonic. If you keep it going, not only the 5, but if you take 7 notes, we end up with the Dorian mode, which is the diatonic scale, the major scale, but starting in D. So already here we see that this is the basics of the diatonic music, Western music. This is how we use until today. And if we keep it going, so we're now using the 12. We see that this is the chromatic scale. So we have all the 12 semitones of the chromatic scale from D to D. So it's very interesting to see how this ratio study of Pythagoras, we can have the pentatonic, we can have the diatonic, and we can have the chromatic scale. So after this, if you keep going, it starts repeating itself in terms of notes, not in terms of the mathematical relation. But if you convert the mathematical relation to the notes we use today, it will repeat itself. And so yeah, going over again, Pythagoras had this idea to experiment with the ratios of strings with different lengths. So it's the same string, the same tension, but different lengths. And then he's checking the sound, and he found out that the unisono is a ratio 1/1. An octave was a ratio 2/1, and it gave the most pleasant sound to the ears. And the second ratio that amazed him was the 3/2, which is the perfect fifth. And he based all this process of using the perfect fifth, so the ratio 3/2, to get notes inside these boundaries, which was a ratio 2/1 inside an octave. With this, we do this experiment, and we see that we get a chromatic scale, what we use today. So we have all the notes from C, C sharp, D, E flat, which is a D sharp, F, F sharp, G, G sharp, A, B flat, which is an A sharp, B, and C. We have all the notes of the chromatic scale. We have all the notes of a diatonic scale. In this way, how we constructed, we came out with a Dorian of D, which is the same as Ionian of C, which is the major scale of C, and which are the white keys in a piano, and that's it. I hope you enjoyed it. I went very, very briefly, not to scare you with equations, but you've seen how to use sympy to perform some very basic symbolic operations. So we solve this ratio for f1, and it just like f2 goes there, multiplying. We also substitute some values, so we get a ratio 2 by 1. We get the frequency of the D3 was 146. We substitute everything here, and we get the new frequency. We convert the frequency to a node, so we have a D4. We have a function to do this ascending and descending transposition of perfect fifths, and if it goes outside the interested octave, we just transpose it back again to inside the octave. And by doing this process, we got the pentatonic, the major pentatonic of C. We got the major scale of C, the diatonic scale, Ionian Greek mode, and we got all the 12 semitones that builds up the chromatic scale. So that's it. Feta, Guitars AI GitHub, Guitars AI YouTube channel. You can take a look in the code, experiment, listen to the MIDI, and check you later.